Hello everyone. So today's tutorial 6 video for the course Trustworthy Machine Learning 2026, and today I will be presenting you with the assignment 3 for the course that is based on adversarial ML. Before moving forward, let's first look at some general announcements. Assignment 3 also requires you to submit a zip submission on CMS in addition to the leaderboard submission. Similar to assignment 2, your zip file must contain a report with maximum 2 pages ICLR template that is already present in the task description. We do not require any abstract. Make sure you add your and like your teammates matriculation number, your team's CMS ID, your how do you approach the task, your results, why did you choose certain hyperparameters, certain ideas, conclusion on the practical implementation of the adversarial vulnerabilities. A detailed explanation of this is already on present on the task description. Make sure that every experiment that you mention in the report, the corresponding clean code is present in the zip submission in the code that you submit. There should be a README file explaining how to reproduce your best leaderboard result. Make sure you avoid adding any model weights or large artifacts. Deadline for both leaderboard and CMS is 16 June 23:59. No exceptions here. Moving forward, let's recap a little bit of adversarial ML to understand the assignment better. We know that during training, models learn to classify inputs by picking up on patterns in the pixel space. The problem is that there are small, certain carefully chosen perturbations in the same pixel space that can push the model predictions scores across a decision boundary without changing how the image looks like to a human vision. And these perturbations are not actually random noise. They are computed using models on gradients by finding the direction in the input space where the loss is maximized. This is what makes them effective with such tiny changes. Here on the slide, you can see a similar adversarial example. The original image here is classified correctly with the classifier as bull mastiff with a confidence of 92%, 95% confidence. The middle image here shows a perturbation, which is just enlarged 100x for us to be able to see the noise. The adversarial image on this right here looks identical to the first one, but is now classified as tiger cat after this particular perturbation is applied to it with a confidence of 19%. Here you can see this is the threat you are defending against in this assignment. Basically, this adversarial examples are the input to the ML model, and they are intentionally designed by the attacker to fool this model into producing incorrect output, and there are very harsh actions to it. So, diving a little deep into how these attacks are, um, the key insight here that we already have seen is the model's own gradients are used to find the direction which is maximizing the loss. FGSM here does this in like a single step. We compute the gradient of the loss with respect to the input, take its sign, and move the input by epsilon in that particular direction. This is fast, simple, and because it's just one step, it can sometimes miss the actual better perturbations. So it is improved by a random start, R plus FGSM. This improves this by adding a small random perturbation before the FGSM step. This avoids starting from the same point every time and helps find more effective adversarial examples. BIM takes this further in regards that it is repeating FGSM, but instead of taking one step at a time, it's taking multiple smaller steps, step size, which is also mentioned as epsilon here or alpha, you can say. Each step size results in the project. Each step size, the result is projected back into the allowed perturbation region so that the total change is going to stay within the budget. And this iterative refinement produces much stronger adversarial examples than one single step. And PGD year, projected gradient descent, is essentially BIM with multiple restarts. You run the whole iterative process from several different random starting points within the epsilon ball and take the worst case result. This makes it harder to get lucky and avoid the attack. PGD is considered the gold standard first order attack, and this is what the robust models are generally evaluated against. The pattern here is clear. Each method builds on the previous one, making the attack progressively stronger and harder to defend against. So, what the assignment here is, you are given a train.npz file that has 50,000 labeled images. Each image is of shape 3 cross 32 cross 32, channels height and width, and each of them belong to one of the 9 classes in the integer range 0 to 8. The images are already labeled. What your task is, you have to train a robust image classifier using one of the uh, allowed architectures, ResNet 18, ResNet 34, or ResNet 50, and it should be able to defend itself against the adversarial examples. What you are supposed to submit is the weights of this robust classifier, also called as the state dict of your model, as a .pt file. And the evaluation that is happening on our end is, we load your model, run the adversarial attacks on our side to check how strong and robust your model is. You do not know what exact parameters that are used on the server for evaluating your model. The goal here is to make sure that your model is genuine, robust, and not overfitting to any one specific attack. That is why you don't have access to the exact attack parameters. One of the strict requirement here is that the model you submit must achieve at least like more than 50% accuracy on our test set. What clean accuracy exactly means is what I'll explain it in the evaluation metric, but you just have to make sure that the clean accuracy is above 50%, and it will be evaluated on a test set. The test set is coming from the same distribution as the train set that is provided to you, so there would be no distributional shifts there. What you are supposed to submit is the model state dict. That is just the weights of the model, but you have to make sure that your model outputs 9 raw logits, one for each of the class, as the usual models do, but they should be raw logits, no softmax or any activation functions applied to it. The input to the model must be 3 cross 32 cross 32, same as the image size. You are supposed to submit the state dict, not the full model instance. And you have to also specify which architecture you are using, ResNet 18, 34, or 50. How exactly you set it, you specify that in the architecture is shown in the code walkthrough. And also an additional slide is present on how to exactly submit it. Moving forward, a TLDR, your task is train an image classifier that is robust against the adversarial attacks that we apply on our end. After you submit your model state dict, higher the score you achieve, better more robust your model is. The clean accuracy should be above 50%, or your submission will be rejected. What you have to submit is a model state dict and name of the model architecture that you used. The public leaderboard, similar to previous assignment, will show 30% of the test data, which you can, this is the leaderboard that you see during your assignment duration. Private leaderboard is the result on the remaining 70% of the test data. This is what you see after the assignment deadline. Make sure to not overfit the public score, and the deadline is 16 June 23:59, that is end of the day. The evaluation metric here, the metric is combination of two things, clean accuracy and robustness accuracy, both are equally weighted. Clean accuracy here is the standard classification accuracy that we are going to evaluate your model on how correctly it classifies the clean samples out of the total clean samples for basic accuracy. inferenced on the unperturbed test images, clean images. The second part is the robustness accuracy. Here we inference your model on the adversarially perturbed test images generated by different attacks, different, like, basically test your model's accuracy on different types of robustness attacks. And it's also the classification. It's also kind of a classification accuracy itself, just on the adversarial samples rather than the clean samples. Both are equally weighted, so make sure that you are giving equal weightage to clean as well as robustness score. You cannot ignore any one of the accuracy. You need to balance them nicely. There is also a trade-off usually that is seen between the clean accuracy and robust accuracy. So when you are training your model using the standard training without any actual adversarial robust training, you often get clean accuracy, but now your model is very uh, sensitive to any of the adversarial data, adversarial example, basically near zero robust. That is the blue here. If your model is somewhere here, that is you have trained it well adversarially, ideally the clean accuracy will be lesser than for what you have for the standard training, but your model is now meaningfully robust. This happens because training it robustly actually sharpens your decision boundary, which makes it a little uh, low, like lesser clean, but more robust. Going forward, now let's look at the actual code walkthrough, what and how you are supposed to submit everything. So if I, okay, first we start with the let's start with the task description. So this task description is already provided to you. You are supposed to train the image classifier, robust against adversarial attacks. You are given the training data set as an NPZ file. The link is already attached on how can you download and access it. What exactly is an NPZ file? I'll explain it in the task template description. You don't have access to the private test set or the attack parameters or implementation that we're doing on the server side. The allowed architecture model is ResNet 183450. The evaluation matrix is a combination of two scores. And the starting point is from the task template. Let's look at it now. So this is already provided to you. The basic imports, torch, data loader, tensor dataset. You can get the ResNet models from Torch Vision mod using Torch Vision models libraries. ResNet 1834 and 50 are the allowed ones. You are provided a train.npz file that your is how it's loading. Just make sure you are adding your correct path to the training dataset here. The dataset here today is provided as an NPZ file. It is basically a compressed NumPy archive. It contains two arrays wrapped together. The first array is the images, that is uint8 array of shape 50,000 cross 3 cross 32 cross 32. Uint basically means the values of the image pixel. Image values are between 0 to 255, the pixels. Labels for every particular image. The corresponding labels are provided in the labels array. The labels range from 0 to 8, total 9 classes. This is how you are loading. This is how you are loading the train.npz. This is where you are converting your images from 0 to 255 range values to 0 to 1 float values, because that is how the model expects it. You are loading the models. Tensor dataset is you're wrapping your images and labels into a dataset object, which is then provided to the data loader along with the batch size and the shuffling and other parameters for providing it to the model for training. Some checks here. The dataset size here will be 50,000 cross 3 cross 32 cross 32. image shape will be 3 cross 32 cross 32. Um, Technically, it should be 50K cross 3 cross 32 cross 32. Labels ranging from 0 to 8, basically total 9 classes. This code here just explains how to load one of the ResNet models. Weights equal to none is basically you are just picking up the unpre-trained model, just the architecture of ResNet 18. Model FC and in linear, here you are basically replacing the last output layer of the original ResNet 18 with what you require, that is the features, and the num class is 9. So it has to the output shape would be 1, like 1 to 9, 9 raw logits. For similarly, you can load ResNet 34 or ResNet 50, whichever you require. Here is a sanity check. You are loading the model in the eval mode, not the training mode. And for a random image, we are checking what the output shape is. And the output shape here will be 1, comma 9. How to save the model? The model is supposed to be saved only as a state dict, that is torch.save model.stateDict, and it will be saved with the name model.pt. Make sure it is model.stateDict and not just model. If you just keep it as torch.save model, it will save the full instance of the model, like the full model object along with the architecture and the weights and every other details, which is not required. It will lead to a rejected submission. Make sure it is just state what you are submitting. Going to the submission.py, what this file is doing is basically a submission script for your robustness task. The imports, again, some details, requirements, architectures, which is already explained to you. What you are supposed to change here is the API key. It is already provided per team. Add the path to your model, like add the path of your model here. Model name, make sure model name is same as what the state dictator uh, says. It's accordingly to that. If your model is ResNet 18, make sure it's ResNet 18. If something else, then it's ResNet 34 or 50. Make sure the submit is always true to enable your submission. That is all you have to do here. No other changes are required. Going back, again, the same thing that I explained in the code walkthrough. These are the three fields that you are supposed to change. Make sure the model name is actually matching the architecture, the state dict that you are submitting. Every submission, you can submit once per every 60 minutes, similar to previous assignments. If your submission is fail or being rejected due to some error on your side, the cooldown is only 2 minutes. So you can submit again after the 2 minutes. That is it. Now let's look into some of the baseline attacks that you could try. A model here trained on only clean data, as we saw in the trade-off graph, would have like a near zero robust accuracy the moment we are going to run any adversarial attack on it. So the simplest baseline that you can try is FGSM adversarial training. The idea is kind of straightforward. For each batch during training, instead of just training with the clean images, you generate the adversarial version of each image using a single step gradient and train on that. You compute the gradient with the loss with respect to the input, take its sign, move the input by the epsilon in that direction. Epsilon here is your perturbation budget and how much you are allowed to change the image. This is fast to compute, but sometimes it may produce weaker adversarial results. It is a good starting point, but you can do better. And that better would be moving one step forward, do a PGD adversarial training. It follows the same idea, just instead of one big step, you are taking multiple iterative steps and projecting the projection back into the epsilon ball after each step, so that to make sure that you are not you are under you are using your resources under your budget, within the budget. And this iterative process will produce much stronger adversarial examples during the training, which means your model will have to work harder to classify them correctly. Hence, the clean accuracy drops a little, but the model becomes more robust. Things you can tune here are the epsilon, the step size alpha, ratio of clean to the adversarial samples you are using in each batch, etc. And that is it. Some of the other baseline results that you can try are actually also provided in the references of the task template. How I have already explained how to submit your results and the submission format. Make sure you look into this. Most of this check is already present in the task.template in the sanity checks. So make sure you run that and check it properly. The leaderboard page is available to you now. And you are supposed to submit a zip report as well as code repository. Make sure to add in your conclusion the answer to the particular question. Try to answer this, that what are the practical implications of the adversarial vulnerability that most of these real world systems would have, and why should we concerned about that. The code repository should contain all your code files, well documented, clean. Every experiment mentioned in the report must have the corresponding code in the repository that you submit. Avoid including large artifacts in your repository. The template file ICLR link is already provided, and there are some references that you can check out. That's it from my end today. If you have any other doubts or questions, please let me know. I will be creating one thread on the forum initially, so that you can ask any questions related to the assignment there. And thank you so much. Best of luck for your assignment.